So previously we have seen the variation of vapor pressure with the temperature. So mathematically we can correlate this variation of vapor pressure with the temperature by using this Clapeyron equation. For the derivation of Clapeyron equation, he has considered the two phases, that is vapor phase and liquid phase, and the change in Gibbs free energy due to change in the temperature for the given two phases. It has been correlated by using this Clapeyron equation. Okay, so simply he has made the change in the temperature. So due to the change in the temperature, there is certainly the vapor pressure of the given two phases will going to change. So as the vapor pressure changes, that means that the Gibbs free energy change will also be observed for the two phases. Okay, so consider the liquid system which is in equilibrium with its vapors. If the temperature of liquid phase is being changed from T to T plus dT, and the pressure is changed from P to P plus dP, therefore the molar free energies of the phase A will become what? Gives free energy at state A, that is initial, plus dGA, which is the change in the Gibbs free energy due to the change in the temperature. And for phase B, consider it is the phase of vapors, so it will be the GB plus dGB. Okay, since at equilibrium the Gibbs free energies are equal. Okay, so we have seen this already, that Gibbs free energies at equilibrium will be equal with each other. So we can say that the GB is equals to GB. Okay, and we can simply put that in this equation, so that we can say that dGA is equals to dGB. Okay, so that is the important relation that we have obtained. But we know the formulas for dG. Okay, that is change in Gibbs free energy, like we have obtained these formulas for the so many times. That is dG is equals to what? VdP minus SdT. So this is the one standard formula that we are going to use here. So dG is equals to VdP minus SdT. Okay, now for the phase A, or the for the liquid phase, instead of this GA or G, we will substitute GA. Okay, so for volume VA, and for entropy change it is SA. Okay, similarly for GB it is dGB is equals to VB dP minus SB dt. Okay, so substituting that values in the equation number 1, suppose that is our this equal equation. Okay, so we have just simply substituted that values and rearrange the equation. So after rearranging, we get that dP upon dt is equals to delta S upon delta V. Okay, that is the change in entropy upon change in volume. So now we have know the one important relation, that is the change in entropy for the phase transition from the liquid phase to the vapor phase are related with the equation, that is delta H upon T. Okay, that is the molar enthalpy of vaporization. There is a one relation, that is delta S, second law of thermodynamics, Q upon T. So for the phase transition, instead of this heat change, we will consider the molar enthalpy change. Okay, molar enthalpy change. So that is the important relation that we are using here. So finally we can say that this dP upon dt is comes out to be delta H upon T delta V. So this is the famous equation which is known as a Clapeyron equation, and it will give the variation of vapor pressure of with the liquid vapor phase with the temperature. Okay, so this equation can be used to study the phase transition. So this is the phase transition for the liquid and vapors. Okay, so if delta H is being the molar enthalpy of transition and delta V be the change in volume, but in the case of liquid vapor equilibrium, this delta H is nothing but the enthalpy of vaporization. So simply we can say that delta H is being the enthalpy of vaporization due to the change of liquid to vapor phase, and the volume delta V will be the what? Difference in the volume of gas and difference in the volume of liquids. Okay, that is Vg minus VL. So new equation will be what? That is dP upon dt is equals to delta HV upon T into Vg minus VL, that is volume of gas and volume of liquid. Okay, so that is the Clapeyron equation. So next modification in this equation is the Clapeyron Clausis equation. So what he has done is the simply he has elaborated or expanded this equation for the ideal gas. Okay, so he has used the ideal gas equation for the gas phase. Okay, because we will generally apply this ideal gas equation for the gas phase only. So this Clausis has applied the gas law, ideal gas law, for the vapor phase and derived the this new expression or integrated form of this Clapeyron equation. So we will see that also. So for the process of vaporization and the sublimation, one of the phase which is being the vapor, which can be expected to obey the ideal gas laws. So Clausis has shown that by applying the gas laws to the vapor pressure, molar volume of the gas can be expressed in terms of pressure. Okay, so for the vaporization process, the Clapeyron equation can be given by what that we have seen the last equation, that is delta hv upon T into Vg minus VL. So as the temperature is being not near the critical point, so we can say that critical point is what, where this gas phase and liquid phase are in the equilibrium. If the temperature is not being in the critical point range, then we can certainly say that the volume of gas phase is always higher than that of the volume of liquid phase, so that we can say that this difference is nearly equals to the volume of gas phase. So next is the dp upon dt is equal to delta h v upon T into Vg. But from the ideal gas equation, we can have the values for this Vg, that is volume of a gas, which is comes out to be what, RT upon P. So just simply substitute that values in this equation, that is dp upon dt is equals to delta hv upon RT square into P, or dp upon dt is equals to delta hv upon RT square into dt. So simply rearranging that equation, or we can say that this dp upon P can be expressed as what, derivative of ln of P. Okay, derivative of ln of P, this dt again taken on the left hand side. So finally we have got the Clapeyron Clausis equation, that is dt upon dp of ln of P is equals to delta hv upon RT square. Okay, so this is the important Clapeyron Clausis equation. Now for the further simplification, he has just integrated by using the proper limits. So we can say that this integration, that is integration from P1 to P2 for d ln P is equals to delta h v upon r into integration from T1 to T2 for the 1 upon T square. Okay, 1 upon T square. So what is the integration of this? It is simply this derivative and integration get cancelled out, so we have been left with only ln of P, that is ln of upper limit, that is P2 upon P1. Okay, and for here right hand side we will use this integration of 1 upon x square formula. So for t square it is comes out to be minus 1 upon t. So here upper limit is kept on the right hand side, it is 1 upon t2, and here 1 upon t1. So for the logarithmic calculation we can simply multiply by using the 2.303. So this is again an important form of, or important expression for the Clapeyron Clausis equation, that is 2.303 log to the base 10 of P2 by P1 is equals to delta hv upon r into 1 upon T1 minus 1 upon T2. Okay, so this will equation will gives you the change in the vapor pressure from P1 to P2 at temperature changes from T1 to T2. Okay, so the vapor pressure of water is 70.12 kilopascal. So consider the problem which vapor pressure of water is being one vapor pressure, that is 17.12 kilopascal at 90 degrees centigrade, and we need to find out the vapor pressure for the same liquid at 100 degrees centigrade if the enthalpy of vaporization for water is 40.81 kilojoule per mole. Okay, so all the values are given, we need to just find out the P2 values. Okay, we need to find out the P2 value. So this P1 is given, which is what, 17.12 kilopascal. We need to find out the P2. Temperature 1 is given as 90 degree, which is comes out to be 363 Kelvin, and this T2 is 100 degree, which is 373 Kelvin. Delta HV is given as a 40.81. So just simply substitute that values in the Clapeyron Clausis equation. So you will get the values of P2, which is around, comes out to be the 100.76 kilopascal. Okay. Now consider the next problem, that is the boiling point of a liquid is 120, that is okay 120 degree centigrade at 96.65 kilopascal. The enthalpy of vaporization for liquid is this much. So find the normal boiling point. So here the pressure to value is not given. So what will we take the first pressure? So we need to take the 1 atmospheric pressure, which is what, which is 1.01 into 10 raised to 5 pascal, or 101.325 kilopascal. Okay, so in the problems you might be given the standard condition. So standard condition you should know. Okay, that is, standard condition is the temperature. What is the temperature? So standard condition for temperature is 27 degree centigrade. Then for the atmospheric pressure, we can say that it is a 1 atm, or 1.01 into 10 raised to 5 pascal or newton. Okay, newton meter. So likewise you should know the standard values also. This gas constant is also joule. Okay, it is in the joule, but this energy is given in the kilojoule, so we need to again convert this into the kilojoule. So likewise there are the certain small concept are there that we need to use during the solving some numericals. Okay, so this 2.303 into log to the base 10 of P2, that is 1 point or 101.325 divided by 96.65, which is delta HV. What is that? 34.31 kilojoule per mole. And here also 8.314, which is the R value, but its unit is what? Joule per Kelvin per mole. So we need to convert that using kilojoule into kilojoule, that is by simply multiplying by using the 10 raised to minus 3. Now next is to, we need to find out the temperature T2, which is comes out to me 394.62 kelvins. Okay, so next problem is based upon the Clapeyron equation. Okay, so you just go through that problem. Okay, that is the Clapeyron equation. So we will start with the new concept, that is the partial molar properties. Okay, in the next lecture.